Welcome to 2026. We have officially moved past the flag planting era of space exploration. Space is no longer just about the temporary visit, it is now about building permanent, sustainable infrastructure. From lunar modules to deep space relays, our focus has shifted from exploration to habitation and industry. NASA's Artemis missions have successfully reached a major milestone, the establishment of the Lunar Gateway. This modular space station orbits the Moon, acting as a vital hub for deep space exploration and lunar operations. By serving as a staging point, the Gateway allows for sustainable research and missions beyond the Moon's surface. The space between Earth and the Moon is no longer a silent void. It is rapidly becoming a bustling cislunar economy. This new frontier supports vital industries, such as autonomous satellite servicing to extend hardware life, and orbital fuel depots, which act as the gas stations of the solar system, providing the infrastructure needed for deep space transit. By managing logistics in this region, we transform how we operate in space, shifting from temporary visits to permanent economic presence. Deep space exploration faces a massive hurdle: the gravity well of Earth. Every kilogram of fuel or water we launch from our home planet costs thousands of dollars and immense energy. To thrive in space, we are shifting to in situ resource utilization, or ISRU. Instead of hauling everything from Earth, we extract it directly from the environment. We mine lunar water ice, split it into hydrogen and oxygen, and transform it into rocket propellant right on the Moon's surface. By turning extraterrestrial ice into fuel and oxygen, we break our dependence on Earth and create the infrastructure needed for deep space travel. The Moon is no longer just a destination, it is our primary training ground. At the lunar South Pole, the Artemis Base Camp serves as the ultimate proving ground for humanity. Here, we test closed-loop life support systems. These technologies recycle air and water with near-perfect efficiency, a necessity for the years of isolation required for deep space travel. By mastering survival on the lunar surface, we are essentially building the survival manual for the Red Planet. We are currently witnessing a pivotal shift in space exploration. While the Moon serves as our laboratory, our sights are firmly fixed on the horizon of Mars. Robotic pioneers are already on the Martian surface, acting as the vanguard for human arrival. These advanced rovers are testing critical life support technologies in the harsh red landscape. A key focus is in situ resource utilization. By extracting oxygen directly from the thin carbon dioxide atmosphere, we are solving the most difficult hurdle of deep space travel: sustainability. This infrastructure is essential for the first human missions, which are now being planned for the late 2020s. We are not just visiting Mars, we are preparing to stay. Deep space missions face a major hurdle: time. Currently, chemical rockets require 7 months to reach Mars. During this time, astronauts are vulnerable to high levels of cosmic radiation. Nuclear thermal propulsion changes the game. By using a nuclear reactor to superheat liquid hydrogen, we generate significantly higher exhaust velocities than chemical engines can achieve. This boost allows us to slash travel time to just 3 months. A shorter trip means drastically less time spent in deep space, protecting the crew's health and increasing mission safety. The International Space Station, a marvel of global cooperation, is nearing its retirement. As we look to the future, the focus is shifting from government-led exploration to sustainable commercial infrastructure. Companies like Axiom Space are developing modular commercial stations. These platforms are designed for agility, supporting everything from advanced medical research to space-based manufacturing. These stations offer unique environments for microgravity manufacturing, such as printing human organs or creating perfect fiber optic cables, impossible to produce under Earth's gravity. Venturing into deep space is not just a technological challenge, it is a biological one. As we aim for the Moon and Mars, our understanding of human health in partial gravity is evolving rapidly. Gravity defines our anatomy. On Earth, our bones support our weight. On the Moon or Mars, partial gravity significantly reduces that load, leading to rapid bone density loss if left unmanaged. Beyond gravity, deep space radiation poses a constant threat. Current research focuses on advanced shielding materials and habitat design to protect astronauts during long duration missions. By mastering these health challenges, we aren't just visiting the stars, we are learning how to live among them. Low Earth orbit is becoming crowded. Thousands of satellites now form mega constellations, providing global internet and Earth observation data. With so many objects, space situational awareness is vital. We must track every orbit to manage traffic and prevent accidental collisions. Even a single collision could trigger a chain reaction. Detecting these threats in real time is the biggest challenge for space sustainability. Low Earth orbit is getting crowded. Every satellite we launch contributes to the growing density of objects traveling at thousands of miles per hour. The Kessler syndrome is a theoretical scenario where the density of objects in orbit becomes so high that a single collision triggers a chain reaction. These collisions create massive clouds of high-speed debris. Each piece of shrapnel can then strike another satellite, creating even more debris. This creates an exponential cascade. If left unchecked, this field of debris could render specific orbital paths completely unusable for future generations. Low Earth orbit is becoming crowded. Thousands of inactive satellites and fragments of debris pose a constant risk to our active space infrastructure. Active debris removal, or ADR, is the next frontier of space engineering. We are building specialized autonomous craft designed to intercept and safely deorbit dangerous objects. These machines use robotic arms, nets, or magnetic tethers to capture dead satellites before they can cause a collision. Once captured, the ADR craft lowers the debris' orbit, sending it into a controlled re-entry where it burns up harmlessly in the atmosphere, keeping our orbital highways open. We now turn our gaze far beyond our own neighborhood. The Habitable Worlds Observatory is our next giant leap in space exploration. The HWO is designed to overcome the ultimate challenge of astronomy, directly imaging Earth-like planets orbiting distant, blindingly bright stars. By masking the glare of the central star, we can finally capture the faint light of an exoplanet and analyze its atmosphere for telltale biosignatures. These light patterns hold the chemical fingerprint of oxygen, methane, and water, possible indicators of biological life. For the first time, we aren't just mapping the heavens, we are actively searching for neighbors in the vast cosmic dark. The global space economy is rapidly maturing, projected to hit $1.1 trillion by 2030. This unprecedented growth is powered by two massive sectors: universal broadband connectivity and the strategic extraction of lunar resources. Mega constellations are revolutionizing global communications, turning the space above us into a high-speed data network. Simultaneously, the race is on to mine the moon's regolith for water and fuel, establishing an entirely new supply chain beyond Earth. We are witnessing the transition from mere exploration to permanent, profitable infrastructure in space. The future of interplanetary travel begins at the lunar South Pole. Automated rovers are currently surveying the surface to map high-concentration volatiles, specifically water ice trapped within the lunar regolith. Once identified, these icy deposits are extracted and processed. This regolith isn't just dirt. It contains the hydrogen and oxygen necessary for future interplanetary refueling stations. By mining the moon, we create a vital pit stop in deep space. This in-situ resource utilization allows us to venture further into the solar system without the massive weight of fuel launched from Earth. On the moon, a single day-night cycle lasts about 28 Earth days. This means 2 weeks of harsh, freezing darkness, which makes powering a base extremely difficult. At the lunar South Pole, unique geography creates regions known as peaks of eternal light. These high-elevation points are constantly bathed in sunlight, even when the rest of the surrounding craters are in deep shadow. By targeting these specific locations, we can optimize solar power generation and maintain constant operations, effectively bypassing the challenge of the long lunar night. These peaks serve as the ultimate power source for future lunar infrastructure, transforming the way we establish a permanent human presence in space. Deep space missions represent the ultimate frontier for human psychology. Unlike missions near Earth, a crew traveling to Mars or beyond experiences total physical isolation. As the mission progresses, Earth becomes nothing more than a faint speck of light in the distance. This Earth out of view phenomenon can significantly impact the crew's sense of grounding and belonging. We are currently researching how crews manage mental health in these confined habitats. Constant monitoring of circadian rhythms, group cohesion, and cognitive load is essential for mission success. By developing robust strategies for isolation, we ensure that while the crew travels through the void, their mental health remains intact. The 2026 space model is defined by a massive shift, moving from the government-only era of Apollo to a vibrant synergy between public agencies and private firms. NASA sets the mission goals and safety standards, while private partners inject rapid innovation and capital to lower the cost of orbit access. This collaboration has turned space from an expensive government-held monopoly into a competitive, efficient market. It's not just about reaching space anymore. It's about staying there. Deep space is filled with invisible dangers. Solar flares and high-energy cosmic rays threaten the health of astronauts during long-haul missions. Traditional shielding is too heavy for extended transit. The solution lies in advanced, lightweight polymers and hydrogen-rich nanomaterials. These new materials act as a kinetic barrier, scattering radiation particles before they reach the crew compartment. Advancements in material science are not just upgrades. They are the foundation that allows humanity to journey deeper into the solar system safely. Low Earth orbit is becoming crowded. With thousands of satellites currently in operation, the risk of collisions has never been higher. Without oversight, satellites move in uncoordinated paths, creating high-velocity collision threats that could render orbits unusable. International bodies like the United Nations are now establishing universal traffic protocols, effectively creating lanes for satellites to ensure safety. Just like air traffic control on Earth, these rules are essential to maintaining a sustainable and accessible orbital environment for the future. The long-term success of our exploration depends entirely on sustainable practices. If we carry our history of industrial pollution into space, we risk destroying the very environments we aim to call home. Currently, orbit is becoming cluttered with defunct satellites and debris. This pollution threatens future navigation and the viability of low Earth orbit. True sustainability requires closed-loop systems. We must recycle every drop of water, every ounce of air, and every mineral resource. This is not optional. It is fundamental for survival in deep space. Sustainability is the bridge to the stars. By ensuring we live in balance with our environment, we secure the future of humanity among them. We are standing on the precipice of a new epoch. We are on the verge of becoming a truly multiplanetary species. By the end of this decade, the moon will no longer just be a destination, but a permanent, thriving base for human civilization. And as we master living off the land, Mars becomes our next great horizon, our next true destination. The future is no longer just in the stars. It is under our feet, waiting to be claimed.